So blues like that actually happen. I don't know how you can use it. I put this on the real close.
Honestly, I should have taken it. I actually kind of forgot about that. I haven't studied for it.
I did it somewhat. I'm just gonna say tonight. I'm gonna watch some of that. Honestly, just yeah. I wanna watch some of that. Since I've done
I learned about that in Pakistan.
I'm not, we can always do more fasting.
Okay, good morning everyone. Quick clarification regarding homework 5. One of you pointed this out to me. I forgot to give you information on problem 2. It's homework 5. Problem 2, the temperature of the ambient fluid on the left side of the wall is 900 degrees Celsius. So T infinity on the left side of the wall. Okay, so please make this correction. Then you should be able to solve this problem. You have your midterm exam coming up next week. That will be opened up on Thursday, and then it will be closed on Friday. In between Thursday and Friday, you have 4 hours to write this exam. You choose your 4-hour window of time. You start your exam. It will be available as a Kalman quiz. Okay, so you start the exam. You have 4 hours to finish it. It's open book, open notes, open web. But please, no collaboration. I trust that you will uphold the integrity of being a student in Ohio State. Okay. In terms of practice for the exam, I would suggest looking through homeworks 1 through 5, including 5, homework 5. Okay. I'll see if I can post a practice exam of sorts on Carmen, and maybe we'll have a review session either this weekend or on Monday next week. All right. The class will be going on as scheduled. Okay, so even though you have your exam which is open from Thursday to Friday, you choose a 4-hour window. On Friday, lecture will still take place as usual next Friday. If you are unable to come, the lecture will be recorded, of course, and you can take a look at it. Okay. Topics for the exam: everything starting from lecture 1 all the way to next Monday's lecture, including next Monday. And I'll send all this information via email. Okay, so it need not just be a verbal communication here. Alright, so that's it for the exam. I want to do a couple more things today, and then on Friday, before I move on to something more interesting, which is called as heat transfer through extended surfaces, called fins. Yes, question.
Will the solutions for homework 4 and 5 be published
Oh,
before?
absolutely. I'll be planning to publish homework 4 solutions either tonight or tomorrow, and then homework 5 will be posted on Tuesday, after you all submit your solutions. Okay. Everything will be available to you on the Kalman page. Okay? Okay. So for today, I want to do 2 problems. One using the idea of contact resistance, and the other is we will start looking at thermal networks for radial heat transfer. Okay, so in a cylindrical and spherical system. So first problem. This makes use of the idea of contact resistance. Right. So I'm pretty sure that a majority of you would have seen a silicon chip. Right? A silicon chip is an integral part of your computing system. And typically as you perform a certain process in your computer or your iPad or whatever it is, there is a certain amount of heat that is generated within the silicon chip because of the transistors of that, right? And this heat has to be taken out, obviously, otherwise the chip will fry. So one of your duties as a heat transfer engineer, Intel is coming to Columbus, so if you're interested in getting a job, you can tell about your heat transfer chops. One of your jobs as a heat transfer engineer is to design a path for the heat to be removed from the silicon chip so that it's maintained at some steady state temperature. Okay? So that's the problem that we're going to be looking at today. So it's a slightly practical problem. Along the way, we're going to make some judgment calls on how deep we want this problem to be. So what you will see is I will present to you the actual situation, and then we will make some assumptions on saying, okay, for the sake of solving this at this point in time, we will do certain simplifications. Okay, so that's our situation here. We are looking at steady state heat transfer, 1D heat transfer. The typical scenario for your silicon chip is the following. Okay, so you have your chip. This is obviously placed on the printed circuit board, which will be insulated. So I'll assume that the bottom of the chip is insulated for all practical purposes. This silicon chip will be surrounded by what is called as an integrated heat spreader. Okay, so IHS. So it looks. Okay, so this is an integrated heat spreader. It has two purposes. One is it protects the chip, it encases the chip in some ways. And then the other thing is it takes whatever heat is generated within the silicon chip and transfers it out. And it is not obviously going to be in direct contact with the chip because there is going to be a thermal interface material or some kind of a thermal paste. Okay, so probably in between here and there. This is an infinitesimally thin layer of thermal paste. I'm just showing it as a very thick layer. Okay, so this is called as a TIM, T-I-M. So this is IHS. This is the thermal interface. Material, okay. It could be a paste, it could be a film, it could be some kind of an epoxy resin, it could be many things. Okay? But it's necessarily there. And this is an infinitesimally thin layer. And we're going to see why this is present today. Then you are going to have a heat sink, which is essentially taking all the heat from the integrated heat spreader and then transferring it on to the ambient, some kind of a convective and radiative heat transfer. This heat sink will be placed on top of the IHS, so this is the sink. And the sink will have some funny looking small protuberances which are called as fins. And the main purpose of these fins, which you would have seen in, if you're looking at radiator systems or if you're looking at exhaust of automobiles and so on, engines, you'll see these kinds of protuberances provided. Their main aim is to enhance the area of heat transfer so that the rate of heat transfer is increased. Okay, so that there is more heat that is conducted out of the body, out of the sink. The sink is typically made of aluminum. One good choice. The integrated heat spreader can be made of copper, it could be made of brass or bronze, one of those alloys. So it could be brass, copper. And the thermal integrated material typically is an epoxy paste or a silicone gel, some kind of a silicone gel or a glycerine gel of some kind. It's also called as a thermal grease. Okay, so this is also called as thermal grease. So this is the real situation, and obviously the silicon chip is printed with the transistors. As you perform a process on a computer, electricity flows into the transistor. The transistor acts like a resistor of sorts. It gets heated up. Depending on the process that is going on, there will be more heat that is generated within the chip, and all of this heat has to be conducted out so that this very thin silicon chip stays at some reasonable steady state temperature, which is again a function of the process that you are performing in your computer. More computation involves more generation of heat. If you are playing a game, some of you play games, you will see that the temperature of your computer is pretty high. Okay? So it's a very practical problem, very nice problem, and in reality it's a very simple problem, as you will see towards the end of the class. Okay? So I'm going to simplify this situation, and I'm going to first look at the following situation. Okay? So simplified case. Just a silicon chip. My symbol for that is S. Then let's say that for practical purposes I don't have this thermal interface material. Just bear with me. You will see why we need that. This is the IHS. You don't want it to be in direct contact with the chip, but let's say for practical purposes it is. And then on top of this is the heat sink. The IHS, let's say, is made of brass, so subscript B. Or bronze, doesn't matter really. And the sink is made of aluminum. Subscript A. Okay, then you have the sink exposed to ambient atmosphere. T infinity and H. I don't show the fins. The main presence of the fin is to enhance the area of our heat transfer, and it also plays a role in how this convective heat transfer coefficient is obtained. All of these things are details that we are not seeing right now, but when we hit convection we will see these things. Okay? So please bear with me until then. Let's also assume that there is a case, perhaps there is a surrounding temperature which is not the same as the T infinity. So let's say this is T surrounding. For the time being, let us ignore T surrounding, but it is there. Okay, we'll see how to incorporate that. That could be radiation heat transfer. Right? So this is the stuff that we are given. We are told the thickness of the silicon layer is 10 millimeters. 1 millimeter, I'm sorry. Very thin, obviously. Let's say that the thickness of the integrated heat spreader is 10 millimeters. And let's say the aluminum sink is 20 millimeters. Right? So this is the thickness of it. 20 millimeters. Now, why we need this thermal interface material is for the following reason. Okay? Let's say that I have two bodies contacting each other. And the fact of life is that you can call a body smooth, but it is never going to be smooth. Surface roughness is a truth that is bigger than you and me. So when you have two bodies in contact with each other, they are always going to be rough, and so they are going to be contacting not through the entire theoretical area of contact, but only at the high points of contact, the aspirative points of contact. Okay, so if I draw two bodies, let's say this is body 2, and this is body 1. Okay, so their contact is going to take place only at the high points of contact, probably here, somewhere there. And so you see that the actual area of contact is really smaller than the interface area that is available to me. And because of this particular fact, I am going to have a temperature gradient at the interface between body 1 and body 2. Okay? So this will tell me that T of body 2 at the interface is not the same as the temperature of body 1 at the interface. I'm going to call it as T2, This is T1. These are temperatures at the interface. The interface is infinitesimally thin, right, in some sense, and you see that there is air gap here. And air is a very poor conductor of heat. So because of this particular reason, what's going to happen is that there is going to be a temperature gradient between the body 1 and body 2 at the interface, and if you would like to model this as a thermal resistance, here is an option. Okay, so one is, let's say that T1 is greater than T2. This is the path of heat flux, okay, passing through. If T1 is greater than T2, if I write a thermal resistance network for this, there are two possibilities. Okay, one is I will have conduction at the point of contact between body 1 and body 2. Okay, so this is T1, this is T2, there is our conduction. They could be dissimilar materials, which will make it much harder for me to use any kind of a formula, because I don't have a formula for when two dissimilar materials contact with each other. What's the conductive flux, right? I have to make use of one and the other and do an energy balance and so on. So we can do that. But there is also another way for heat to travel, which is through the air gap. And so there is going to be conduction through the air gap as well. So this is our conduction air. And usually, as is typical practice in heat transfer, we don't draw the network in this particular manner. We say that there is a contact resistance between the two materials at the interface. Okay, so this is replaced by T1, T2. This is R double prime contact. So R double prime contact is some kind of an empirical value of the contact resistance for some area that you use in the experiments. Okay? So R double prime contact is the contact resistance at the interface, which symbolizes the fact that there is a temperature gradient at the interface. Okay, so whenever you see two things coming in contact with each other, they could be made of the same material, they could be different material, it really does not matter. They are never going to be perfectly smooth, and so there is going to be a certain contact resistance which symbolizes the fact that there is a temperature loss taking place at the interface. Okay? This is a typically empirically obtained value. There is no theory behind it, there is only experimentation, so this is empirical. And very important is the following. When we spoke last time, I did not mention the units for thermal resistance to conduction and resistance to convection. Let's take a look at it. So our conduction is L by K times A. And if you look at the units, let's say SI system. So this is meters, watts per meter Kelvin, and then this is meter square. And you do the simplification, you'll end up getting this to be Kelvin per watt. Okay, this will be the units for thermal resistance. To conduction, if you want to do convection, same thing. Our convection is 1 by H times A, which is 1 by meter square Kelvin, meter square, which is, as you would have guessed, Kelvin per watt. Okay, so this is the unit for thermal resistance. The contact resistance does not have the same units. This is because when the experiments are performed by assuming some kind of a standard area. So 1 meter square is the standard area. Okay, so for 1 meter square of the interface area, what is the contact resistance for a given set of materials in contact? This is how the experiments are carried out. So when you perform the units for R double prime, Please note the symbol, it's different from R. So R double prime has units of meter square Kelvin per volt. What's the role of that meter square? For 1 meter square of interface area, what is the contact resistance? And this is something that is empirically obtained, which means that if you want to bring it to your actual units, then R contact has to be R double prime divided by the area, because your interface area need not be 1 meter square. It could be greater than 1 meter square, it could be lesser than 1 meter square. That depends on your problem. Okay? So this is typically what you'll have to do. And what people typically do is, okay, you obviously see that I have asperity contact, but then there is air here. So rather than have air there, I will rub some thermal paste or thermal grease on it, whose thermal conductivity is obviously better than that of air, so that I enhance the heat transfer going through. And that is the exact reason why we have this thermal interface material. Yes?
How does the thermal conductivity of the thermal paste compare to the thermal conductivity of the metals used in the heat sink and the?
The thermal conductivity of the paste is going to be much lower than that of that.
Okay.
Yeah. And so typically you see that if you're applying a paste, it's a semi-solid or a fluid, so their thermal conductivities are going to be lower than that of the actual materials in contact. But it's going to be better than that of air. Okay? So that's the reason for the presence of this thermal interface material, and in fact, I really need to have a thermal interface material between the heat spreader and the sink as well. For the sake of simplicity, I'm not showing it. Okay? Alright, so now I'm going to model our problem with all these pertinent information present in the form of a contact resistance, and we will have the following values. So this is the situation for us. Silicon chip. There's going to be some heat generation taking place, so Q dot is not 0. Then I'm going to have a thermal interface material, which is an infinitesimally thin strip of either of some kind of a resin-like material. And on top of that is our heat spreader. Okay. Again, these are all shown exaggerated. And so between the silicon chip and the heat spreader, there is a contact resistance. The contact resistance, R double prime, between the silicon chip and the integrated heat spreader. Okay, so this is the silicon chip S, this is V. This is given to us, empirically determined, depending on what you are using as the material for the heat spreader, and obviously silicon here, 0.5 10 to the power minus 4 meter square Kelvin per watt. Okay, so this is given to us. The value of Q dot is given to us as well for this problem. So Q dot is 500 kilowatt per meter cube. Q dot is energy generated per unit volume, internal generation. Presence of the transistors takes care of that. Thermal conductivity of silicon is given to us. Thermal conductivity of the IHS is given to us. Then I'm going to have the aluminum sink. In reality, I should have a contact resistance there as well between B and A, but I'm not doing it. Okay, just for simplicity. And then I'm going to have P infinity and H. P surrounding, and I'm going to write down the values for all of these. Okay, so T infinity is 20 degrees Celsius. The heat transfer coefficient between the fin surface and or the whatever sink surface and the ambient atmosphere is 10 watts per meter square Kelvin. Okay, let's say that the area of contact is 1 meter square everywhere. Meter square. Okay. Thermal conductivities. So K silicon, K brass, K aluminum, have the following values. So 150 watts per meter Kelvin, 110 watts per meter Kelvin, and 220 watts per meter Kelvin. And sometimes, if you're a real pro gamer, okay, which I'm not, I've never played a game in my life. My son does, but I don't. I would like to maybe someday. But if you're a pro gamer, you do what is called as the process of de-lidding. You open up the CPU system, remove this integrated heat spreader that the company has given to you, and then put your own stuff on there, which is having a better thermal conductivity, so that you enhance the mode of heat, enhance the rate of heat transfer. Okay, so all these things can be done. All right, and then I need the thickness information. So L of silicon, 1 mm. L of the bronze or the brass, whatever you use as a heat spreader, this is 10 millimeters. I think I wrote it down there. And then L of the zinc is 20 millimeters. What do we need to find in this problem? And the bottom surface is insulated. Okay. Once again, an approximation of some sort. Not a bad one. Okay, you're making the silicon chip is essentially sitting on the printed circuit board, the PCB, and you can assume it to be insulated. Alright, what do we need to find in this problem? I need to find the temperature at the top and the bottom surface of the silicon chip. Okay, so what is Ts? And I'm going to set up a coordinate system. Okay, going from bottom to the top is positive x. Ts at x is equal to 0 millimeters. X is equal to 1 millimeter. And these are the things that we need to find. The only novelty in this problem is this presence of this contact resistance. Otherwise, this is very similar to what we have encountered in the past. There is heat generation in one portion of the body. The other things don't have heat generation, so the flux has to be the same throughout. And I can make use of the idea of thermal resistance network. Okay? So let's get into this problem. I'm not going to go through the entire details of it because it is, I hope it is obvious to us that if I look at, let me call this as x is equal to 0. This is x is equal to 1 millimeter. Okay, then I'm going to have the thickness. So this is x is equal to 11 millimeters, and that is x is equal to 31 millimeters. Okay, starting from x is equal to 0. If I draw a control surface at this interface, the flux that is coming from the surface x is equal to 1 meter, which is belonging to the silicon, is going to be the same as the flux that enters the brass surface. And obviously there is no heat generation in either of these top two bodies, which means that the flux through them is a constant. Okay? So if I draw this out as a thermal network, I cannot draw a resistance for the silicon because there is heat generation taking place within the silicon body. Okay, but if I draw the next network for the rest of the system, let us assume for the time being radiation is not present. Okay, so assume or neglect radiation, and we'll see what happens if we incorporate radiation. It's kind of a messy thing. I'm first going to have some kind of a convective resistance between the aluminum surface and the ambient. Okay, so this is T infinity. This is our convection. This is temperature of the aluminum at x is equal to 31 millimeters. And then as I keep going further down, I see that the flux is the same. So I can have a resistance network between B and A. In reality, there is a contact resistance. We'll get to it in a minute. Okay, so this is going to be TB at x is equal to 11 millimeters, and there is a conductive resistance in between them. So this is our conduction as I pass through the aluminum body. So this is our conduction A. Then I have the contact resistance. Okay? So I have our contact. Which means that when I'm writing the temperature at the next node, it should be the temperature of the silicon body at X is equal to, I'm sorry, I forgot the conduction through the, absolutely sorry about that. This is conduction here through the brass body, right, through the thickness of that. And then I reach temperature Pb, X is equal to 1 millimeter, and then I have the contact resistance coming in between the silicon top layer and the heat spreader. The silicon, please notice, we are assuming that this contact is going to be infinitesimally small, infinitesimally thin. Okay, so which means I am still using X is equal to 1 millimeter at the contact region, but there is a small resistance or a small temperature drop between the two. Okay, so this is our contact. That's about the only network I can draw. I cannot go further and draw through the silicon chip. I have to do heat diffusion equation inside there. Okay. The path of heat transfer, ambient is cooler, silicon chip is hotter. Our entire purpose is to maintain this chip at some steady temperature, and so the path of heat transfer is going from bottom to top. Alright, and just for the sake of completion, if I draw a control surface at the interface, okay, so I'm going to draw the control surface here. So control surface at the interface. And if I do an energy balance, there is going to be a certain amount of flux coming in due to conduction in the silicon layer. There is no energy generation because I'm doing a surface energy balance, and so this is going to be equal to the flux that is going out through the heat spreader, and X is equal to 1 millimeter. And because there is no heat generation in the bronze and the aluminum pieces, no Q dot in A and B, the following statement is true. The flux is a constant. Q double prime at 1 millimeter is Q double prime B at X is equal to 1 millimeter. This is because of energy balance, right? First law. And then this is equal to Q double prime B at X is equal to 11. This same heat flux is passing through, going to the aluminum sink. Aluminum, which in turn is 31, and this is passed out as convective heat transfer between the ambient and the aluminum sink top surface. So this is the entirety of the problem. Any questions, please? I've been rambling on for some time. Yes, yes.
On our resistance chart, we never talked about the temperature at X equals 0. I guess why don't we?
Temperature at X is equal to 0 is because you see there is heat generation taking place within the silicon chip, and so I cannot really draw a resistance through the silicon because the conductive resistance is defined only when there is no heat generation.
And then, since we're not taking into account surface resistivity for the A and B connection, can we assume that TA equals TB at 11 millimeters?
Absolutely, yeah, yeah. So in reality, there should be TB at 11, this is TA at 11, TB at 11. There should be a contact resistance there, but we are assuming that's not the case. Okay, so you're right in saying this is equal to TA at X is equal to. Yeah. Any other questions? You have a question? He's raising a hand. Any other questions, please? Once again, these are not anything very different from what we've done in the past couple of lectures. The only novelty here is this contact resistance idea, and added to the fact that this is a practical problem, which makes some physical sense. Alright, so with all this information, let's get going with the solving of the problem. We will make use of this, and they should have just removed the wall on the top so that you can see all the three panels at the same time. Alright, so I start off by writing my equation. Okay, this is just a set of resistances, bunch of resistors in series. You just add them up, right? That's as silly as it gets. So I have Q double prime. I can pick any one of these to write my equation that relates the resistance, the temperature drop, and the heat transfer rate. Okay, so I'm going to pick one of them. So this is Q double prime at x is equal to 1 millimeter. Of course, multiplied by the area, right? This is equal to P of the silicon at 1 millimeter minus T infinity by R total. This is one equation that you can write, and in between you can write any different kind of equation choosing any of the two nodes. I can choose this node and I can choose that node, and I can write a temperature Q is delta T by R. Or I can choose this node and that node and then add up the resistances that I see here. So this is just playing games, right? So that's one equation. I don't know anything about any of these things except R total. So let me write R total. Is the contact resistance, first of all, divided by area. Don't forget to divide by area. In this problem, the area is 1 meter square. It need not be the case in any of the other problems. Okay? Plus, I'm going to have conductor resistance. So that's going to be LB KB times A. In reality, as one of you mentioned, there should be another contact resistance between B and A at the interface, but I'm ignoring it. So this is just going to be LA by KA times A 1 by H times A. Alright, so things that I know R total because I know everything regarding the problem parameters. I know T infinity. Okay. Obviously I don't know Ts at x is equal to 1 millimeter. And I don't know this guy as well. Okay. So which means that I go back to the silicon chip because there is heat generation, I use the heat diffusion equation. So look at the HDE. Steady state 1D Q dot is not 0 and the constant. Okay, it's given to us 500 kilowatts per meter cube. So if I write the heat diffusion equation for this situation, I have the following. Okay, silicon d square T plus Q dot is equal to 0. The dt by dt term vanishes. We have done this multiple times. You just integrate this twice. Okay, so integrate twice. Ts of x is minus Q dot 2Ks plus C1x plus C. Alright, so two constants. I have two equations essentially. I can also calculate the heat flux if you like. So Q double prime of the silicon as a function of x is going to be minus q dot minus k silicon times dt by dx. And so q double prime. I will lose the negative sign, right, because I have a minus q dot. C2 will vanish, and so I'm going to have ks q dot x by ks minus c1. Okay, I'm just writing it down because I see that the flux is needed at that particular equation there. So two things. Okay. Boundary conditions. Do we know any boundary conditions? Yes, sir?
At x equals 0, it's adiabatic.
At x is equal to 0, it's adiabatic, so which automatically tells me that this character C1 is going to be 0. Okay? So boundary condition, it's insulated, and x is equal to 0. dt by dx is 0, so q double prime s and x is equal to 0 is also 0. And so if I substitute, this tells me C1 is 0. So if C1 is 0, I can actually calculate the flux at x is equal to 1 millimeter, right? So this tells me Q double prime at x is equal to 1 millimeter is Ks times Q dot x by Ks minus C1 evaluated at this particular value. C1 is obviously 0. Ks and Ks cancel each other off. X is equal to 1 millimeter. Q dot is 500 kilowatts per meter cube. And so if I substitute, Q double prime is 500 watts per meter square. Okay, Q dot is 500 kilowatts per meter cube. 1 millimeter is 10 to the power minus 3 meters, so the kilowatt term vanishes, and I end up getting 500 watts per meter square. Okay? Substitute. So this is, let's say, 2. This is equation 1. Substitute and solve. Solve for T, S. This is equal to, okay, all of these are known except for the temperature. At x is equal to 1 millimeter, everything else is known to me. So this is known, the infinity is known, R total is known, all the parameters of the problem are given to me. This is the only unknown for me. So, to solve Ps at is approximately 70 degrees Celsius. Typical temperature at steady state for your silicon chips is around 50 to 55 degrees Celsius. This means that the person who's employing this is a gamer. Alright, that was the joke of the day. Moving on, right? I need to find the temperature at the bottom surface, which is now fairly trivial because I know the temperature here. I can find out the constant C2. So Ts and x is equal to 1 millimeter. I go back to my quadratic profile which has been obtained there. So this is minus q dot times 1 times 10 to the power minus 3 square, 2 times Ks C1 plus C2, but C1 is 0. We just calculated, right? Ts is known to me. Substitute. Q dot is known to me. C2 can be calculated. So C2 70.8 0.3, so not much of a difference between the top and the bottom. Okay, so perhaps poor design, but or maybe it's good design. All right, which obviously tells me the temperature at x is equal to 0, which is C2, is that value there. So T S at x is equal to 0 is C2, which is 70.02 degrees Celsius. Okay. We solved this problem in Celsius because radiation was not a factor. Now let me bring in our good friend radiation. So what happens if radiation is a factor? Okay. Let's see what happens. Two options here. One is the temperature of the surrounding is different from that of the surface, ambient. Okay, so here I could have the surrounding not the same as T infinity. Typical situation is when you look at an engine block gets really hot due to the combustion reactions. The temperature there is really much higher than the ambient air around. Okay, so that's where radiation becomes significant. The other situation is the surrounding is approximately T infinity, nice balmy day, not much wind. This is a reasonable approximation for most of our problems. So let me draw the thermal network for both of these cases very quickly. So this is case 1, case 2. If I look at case 1, because the surrounding temperature is not the same as the ambient temperature, what's going to happen is that I had the figure drawn. Let me draw this very quickly. Ts at 1 millimeter, Tb at 1 millimeter, 11 millimeter, then this is Ta at 31, this is the same. Alright, so this was the network that we had. We had a contact resistance here. Our conduction. If I did case 1, the heat flux that is traveling through this pipe, traveling through this network, is going to branch off into two because the temperatures are not the same. There's going to be one branch going to the convective region, the other branch going to radiation. Okay, so here, this is T infinity. This is T surrounding. Okay, so the heat flux is going to branch off, goes here, and then goes there. So this is almost like employing Kirchhoff's current law at that particular node. Right, the heat flux that is entering is equal to the heat flux that is the sum of the two of them leaving out. Okay, so that is conservation of charge at that particular node in some sense, or conservation of thermal energy at that particular node. First law, exactly the same thing. And this is our convection, your regular guy. This is our radiation, which we have not seen till today, so I'm going to see it today. So how to get this R radiation? Okay, so let's do that. This doesn't go up. Very quickly, Q radiation is delta T by R radiation. Okay, this is your regular formula. Keep in mind that Q radiation is the net radiative heat transfer rate. Net heat transfer rate, and if I say that radiation is the net heat transfer rate due to radiation is going from the silicon surface or from the aluminum surface onto the ambient, so net Q radiation out, this is going to be area times, remember every surface emits radiation, right, radiant flux that is emitted by the surface, And every surface, because of the fact that it's in proximity with other human beings and other creatures and other surfaces, will receive some irradiation. And a portion of that will be employed to enhance the thermal energy of the body, of the surface, right? And so this is going to be my net radiation heat transfer rate. Bear with me for a few more minutes and we'll be done. If I substitute, this is A times sigma epsilon temperature of the surface to the power 4 minus sigma times alpha temperature of the surrounding to the power 4. And if I employ the fact that this could be a gray surface, so alpha is the same as epsilon. These are all big assumptions. You will see that when we do radiative heat transfer, these need not be the case at all. Okay, this is a huge hole in our thought process which we will fill very soon. So Q radiation is A times sigma times epsilon. I can take them as common factors, and this is something to the power 4 minus something to the power 4, which by making use of some basic algebra is Ts square, T surrounding square, Ts square, T surrounding square, A to the power 4 minus B to the power 4 is A square minus B square times A square plus B square. I have an A square minus B square there, which I split again into two more creatures. So this is A sigma epsilon Ts plus T surrounding and Ts minus T surrounding. Then this is Ts square, T surrounding square, and then that creature. This is just algebra, right? Now, if I compare the two, what is my delta T? Delta T is Ts minus T surrounding. And all of that big thing that I've written there, the inverse of that is going to be my thermal resistance to radiation. Okay? So R radiation is going to be 1 by sigma epsilon A Ts plus T surrounding Ts square T surrounding square, which means that this is a problem. My resistance to radiation is now a function of the temperature of the surface, which I may not know beforehand. It is not just a function of the properties of the surface. If you look at thermal resistance to conduction and so on, they are properties of the surface. They depend on the length, it's a geometric property. They depend upon the thermal conductivity, material property. They depend upon the area, which is once again geometric. Here I depend on the type of the surface, which is epsilon is dictated by how rough the surface is. Is it a polished surface? Is it a diffuse or a specular kind of a surface? Emitter, we'll see all these terminologies soon. Depends on the area. Unfortunately, depends on the surrounding temperature, which would be unknown to me. Depends on the surface temperature, which is just something that I could be solving for really. So radiation is typically not included in the resistive networks. And this is for this particular reason that we ignore this creature and we say, okay, we don't know much about radiation so far. We will have a placeholder for that fellow. When things get better, when our knowledge is more enhanced, we will start including radiation. Okay? So this is what happens if you have the temperatures to be different. If the temperatures are the same, very quickly, until there it's also going to be the same. From here, this is just going to be a parallel network. That's T infinity. This is TA, 31. This is our radiation. This is our convection. And this is for case 2. Okay, and this is for case 1. It's a lot to digest. So we'll come back on Friday, some of us, and then we will look at this very, very briefly. And then we will move on to radial heat transfer. Okay? Yes, sir.